Well, today we're really fortunate to have the project scientist for the Roman mission, Julie McEnery. She previously was project scientist for the Fermi Gamma Ray Space Telescope as well. So there's a lot of talent here. Julie got her PhD in experimental physics from University College in Dublin, Ireland. She's a fellow of the American Physical Society, adjunct professor at University of Maryland and George Washington University. And she's worked with ground-based gamma ray telescopes that detected Cherenkov radiation in her life before coming to Goddard. So an experimenter after my heart. Anyway, Julie is going to tell us about Rome and what to expect in the near future.
Okay, so it's a pleasure to be here. I am going to talk about the Roman Space Telescope mission science. I'm not going to really address any of the technical or engineering details, so if you want to know more, you should have another Roman speaker. So the title of my talk is Getting Out from Under the Lamppost, and that is to reflect that with this observatory, we are going to be doing astrophysics in a different way. And I'll talk a little bit about what I mean by that. So, usually when people start talking about Roman, they talk about Roman has a large field of view. And this is illustrated here, where you see in the center the famous Hubble image of the pillars of creation. The larger image is a representation of the Roman field of view. And what you can see is that if Roman took an observation of this region, you can see the pillars of creation in the context of the broader Eagle Nebula which it's a part. Roman's field of view is more than 100 times larger than Hubble's field of view. But we have the same size primary mirror, so we have the equivalent sensitivity, equivalent angular resolution. But that's not really the full picture, because the observatory is designed to survey the sky quickly and efficiently. So one way of illustrating this is a famous Hubble survey of the Andromeda galaxy, which took over 400 pointings with Hubble, would take 2 pointings with Roman. But the increase in speed is 1,400. So one way to think of Roman is that it's not just that we've got a large field of view, it's that we can survey the sky incredibly quickly. The main survey with Roman, which will take 2 years, would take 2,000 years with Hubble. So when we talk about having a larger field of view, a survey capability with Roman, it's not that we do Hubble science faster, it's that we get to do science that you could not do with Hubble. We get to do the kind of science that you can do when you don't have to know where you're pointing. And that's what I mean when I say getting out from under the lamppost. We don't choose a galaxy and go and point at that galaxy. We're going to map out large regions of the sky, find hundreds of millions of galaxies, and use those to understand everything from the evolution of our universe to the nature and evolution of the galaxies in that universe themselves. We have written down mission objectives, and these are important because the mission objectives are what drives the specifics of the design of the observatory. In one box we have dark energy and the fate of the universe, and this really reflects how by being able to map out large regions of the sky, you can get a sample of the universe that is representative of the universe itself and not of some strange thing that happens in some small region. We will use this observatory to look towards the center of our own galaxy to revolutionize the study of planets around other systems. We can use a technique called the microlensing technique to find planets. I think this is... Okay, I'll keep talking. To find planets around from 1 AU all the way out to the equivalent of the outer part of our solar system and beyond. And this is a region of phase space that is not explored by current missions such as Kepler and TESS. We'll do a wealth of astrophysics with wide area surveys. And then finally, we also have a second instrument that is a technology demonstrator to demonstrate the technologies that will be needed for the flagship mission that will follow ours, the Habitable Worlds Observatory. Okay, so let me start with a brief discussion of our universe. So you may already be familiar with this if you make a pie chart of what is the universe made of. Normal matter, so the stars, the galaxies, the planets, us, make up only 5% of the mass energy content of the universe. Thank you. Also, we have what we call dark matter. And dark matter is, it's matter. We know it's there because we can see its gravitational effect on things around it. And we know from a combination of looking at the motion of stars around galaxies, looking at the motion of galaxies in clusters, and information from the cosmic microwave background, we know that dark matter makes up around 27% of the content of the universe. The third part is the really weird one. In the late 90s, astronomers conducted a sequence of investigations to explore how the universe is slowing down. Because if you think about how you expect the universe to work, if you have a Big Bang, matter is being pushed out in all directions. Gravity pulls things together, so you would think, well, if I have a Big Bang and then everything lets loose, what I'm really measuring is how much is gravity slowing things down. And when they did that, they discovered, to their surprise, that the universe is not decelerating, that it's in fact accelerating. So there is some property of space that is accelerating and pushing things apart. And we call that dark energy, but we don't really know very much about what it is. So if we look at this pie chart, the matter, so dark matter and ordinary matter, has the effect of pulling things together because it primarily operates by gravity. So it's going to tell you how the structure of our universe has evolved as a function of time. The pattern by which the galaxies formed.
I bet you it's a battery, and I don't have a spare.
Okay, that's fine. The structure by how the how galaxies formed galaxies and into clusters of galaxies and so on. And the dark energy is going to primarily drive how the universe expands. Although in fact it's a combination of the two, right? The dark matter is pulling in, dark energy is pushing apart. So the balance of those two is going to address how the universe has expanded as a function of time. So one of the things that Roman is going to be able to do with exquisite precision, more than a factor of 10 better, is to measure these, the evolution of structure in our universe and how the universe is accelerated with time, a factor of 10 better than before. So I'd like to say a little about the kind of observations that are going to allow us to do that. So this image here is, it's a cartoon. And what it's telling you is our main survey, or one of our main surveys, is to look at around 2,000 degrees on the sky. And for comparison, this is the largest survey that Hubble has ever done. Just to give you a sense of the difference in scale. We'll conduct this survey in multiple filters. We'll also have slitless spectroscopy. In this region of the sky, we will measure over 1 billion galaxies. We're going to precisely measure the shape of hundreds of millions of those galaxies. And we're going to precisely measure the distance to tens of millions of those galaxies. So, for example, if I'm measuring the position and distance of tens of millions of galaxies, then I can obviously create a 3D map of the universe where I can map out the position and pattern of galaxies from now all the way back through cosmic time. So if we had to compare ourselves to Webb, if Webb can give you exquisite measurements of close to the beginning of the Big Bang, Roman will tell you what happened next. You know, how the universe behaves since then. So what you're seeing here is slices of the universe from high redshifts, which is large distances or early times, up to the present day. And we will be making these kinds of maps with Roman, but in a revolutionary way, because we have so much more sensitivity than has ever been done before. We can also, from these data, get a measure of the expansion history of the universe. And that's because early in the Big Bang, while the universe was still opaque to photons, photons couldn't escape, there's density waves going through the plasma. And those density waves have a characteristic wavelength. And when the universe became transparent, the pressure was released, so those density waves stopped. But the imprint of those remain in the distribution of matter. So if you take a slice of the universe and you look at the typical distance between pairs of galaxies, you'll find a peak that corresponds to this early characteristic wavelength. And as we move out in time and the universe expands, this gets wider and wider and wider. So you can think of it as like a standard ruler. And we can use this to get a measure of how the universe is expanding versus with time. Another thing that we're going to do, I mentioned that we're going to measure the shape of hundreds of millions of galaxies. I'd like to tell you why that's so important. If you imagine, and this is hugely exaggerated, if you imagine that you've got a population of distant galaxies, and the light from those galaxies is coming to us, but has to pass through foreground galaxies. Those foreground galaxies contain mostly dark matter because the ratio of normal matter to dark matter is very small. The presence of that matter causes gravitational lensing. It causes the light rays to be very slightly bent from the background galaxies to the foreground galaxies, to the background galaxy to what we see. And the amount of that bending, the amount of that deviation is related to how much matter those light rays have to pass through. And this effect is very, very small. So you measure a single galaxy, it's going to look just like a galaxy. But if you measure thousands, hundreds of thousands, tens of millions of galaxies, then you can start to see that, oh, all the galaxies in this region tend to have a shape that's aligned in a particular direction. So you take a large number of galaxies, you measure their shapes, and from that you discover patterns in those shapes that you can deconvolve to get distribution of dark matter as a function of time. But we don't just have that survey. That's just one of the things that we're going to do. Another thing that you can do with an observatory like Roman is to explore the sky in time as well as in space. So one of our other major surveys is to take a region tens of square degrees and go back every 5 days for several years. And with that, we can find everything that's changed. So we'll find tens of thousands of supernovae. That's stars that are exploding at the end of their life. We can find neutron stars that merge together to produce a cauldron of radioactive activity that will produce the light that we'll see with Roman, but also gravitational waves that can be detected by gravitational wave detectors on the ground. We'll detect stars being swept into supermassive black holes and producing a burst of radiation. This connects to cosmology because there's a particular type of supernova that occurs when you take a white dwarf star in orbit around a normal star. As material is accreted onto the white dwarf, when it reaches a critical mass, it undergoes a thermonuclear explosion and has a supernova. And because that thermonuclear explosion always happens at the same mass, you can determine a standard brightness. And if you know how bright something is in an absolute sense, and you measure how bright it looks, you can tell how far away something is. Right? It's, you know, if you take a candle and you move it further away, it gets dimmer. And if you know how bright the candle is, you can measure how far away it must be based on its brightness. So we compare that to a redshift. We have another way of measuring how the universe is expanding with time. And this is, in fact, how we made the discovery in the late 90s about the universe accelerating. But Roman is going to take these measurements out to much, much greater distances than has ever been done before. And one of the advantages of Roman is that we're going to measure the expansion history of the universe using supernovae out further than has ever been done with supernovae before. But we're also going to measure the expansion history of the universe using the large number of galaxies, that 3D map of the universe. And by having multiple ways of measuring this, we will be sure that what we're really measuring is the fundamental nature of the universe itself and not something we didn't understand about supernovae or something we didn't understand about galaxies.
Question, do you know what area of the sky that's going to be focused on? Has that been decided?
No, so one of the, and actually this is a really great question because it ties to what we're doing right now. We require that the surveys do the cosmology that I just described, but the science return is much, much richer than that. We're going to be using those surveys to study clusters of galaxies, to study galaxy evolution itself. This will be an outstanding survey for finding large numbers of brown dwarfs. So we are in the middle of a process to engage the scientific community to define those surveys. So we asked for a set of white papers. We got a large number of really detailed white papers describing how people wanted to engage with all of our surveys. And we're about to set up committees, and over the next year, we will be engaging in a community process to define the surveys. So watch this space, because what's really exciting about this process is, and you asked a really good question, is that we're getting to hear all the things people want to do with our surveys, way beyond our objectives and our requirements, and it's really exciting. And it's very real for the community because we're going to launch in 2026, so we're now within that magical timescale of a graduate student thesis timeline. Right? A student starting now will experience launch just before they graduate, which is nice. So we have multiple different ways of making cosmological measurements. And so far I've focused on the advantage of having a large field of view, the advantage of having a survey capability, but that's not all that Roman does. to measure the very subtle shapes, shape modifications, we have to have a very, very stable point spread function, a very stable observatory. So we can characterize our point spread functions to 1 part in 10,000. We're at an L2 orbit. The observatory is much more stable, so we have far better stability performance compared to Hubble. For the supernovae, because we're critically dependent on mapping how bright something appears to determine how far away it is, we have exquisite ability to accurately map fluxes measured by the observatory into the actual flux that arrived there. So we have exquisite controls as to uncertainties. And I'm going to change topics. So moving into our own galaxy. So what you see here is an optical image of the center of our own galaxy, the Milky Way. The third major survey I want to discuss is looking towards the center of our galaxy, and every 15 minutes cycling around a 2 square degree region of the sky. And 2 square degrees seems kind of small, although it's still bigger than Hubble's biggest survey, but it feels kind of small. But in that region, we'll have several 100 million stars. So we're going to be measuring precisely the brightness of several 100 million stars every 15 minutes for 2 months at a time, spread across the lifetime of the mission. That's going to be absolutely spectacular for studying the stars themselves. You can use those observations for some astroseismology, where the oscillations in the star tells you about the density structure interior to the star. That we have a very stable observatory, that we can measure shapes very precisely, means that we can measure stars' positions very precisely. So we will have astrometry, which is the ability to precisely measure where something is, roughly equivalent to the Gaia mission. But because we operate in the near infrared, we are going to be precisely measuring the distances, speeds, and motions of stars in the galactic bulge, which will provide revolutionary information about stellar astrophysics for that population of stars. The thing that is driving these observations is microlensing. So the idea here is that you've got a bunch of stars in the galactic bulge, which is where our observations are happening. And as the solar system, moves around the galaxy, every now and again you will have a chance alignment between a foreground star and a background star. That chance alignment causes a gravitational lensing that will give you an increase in flux that lasts, let me play this again, that lasts on timescales of days. But if this foreground star has a planet, we'll see in a minute, the little planet also causes microlensing. So if we look at the pattern of brightness from this, apparent brightness from this star as a function of time, there's a spike that relates to the mass of the extrasolar planet. The distance between this peak and that peak, which is no longer there, but you can imagine, is telling you how far away the planet is from the star. Now this matters because missions like Kepler and TESS detect planets via the transit technique. And that's what you might expect, that as a planet moves in front of its star, the star gets briefly a little bit dimmer. And that technique is sensitive to planets that are close to their host stars. So this indicates the kind of region that Kepler and TESS are sensitive to by the transit technique. And this puts it into context of where Roman will see in the purple. So if you combine the transit technique with microlensing, you get the full picture of planets from close to their host star all the way out to the equivalent of the outer solar system and beyond. And that's what you see in this plot here, where it's distance from the host star on the x-axis and planet mass in the y-axis. And here you see where all the Roman planets detected by microlensing would be. And you can see, because superimposed are images of the planets in our own solar system for context. So that's great. So you think, okay, fabulous. We're going to complete a census of planets around another solar system. But it's not the full story. Because we can also detect planets via the transit technique. So not only is Roman going to complete the picture of the distribution of planets around other stars, we're also going to increase the total number of planets seen by more than an order of magnitude. So one way to think of this is that what JWST is to Hubble, Roman is to Kepler. That we are going to revolutionize our understanding of the distribution of planets around other stars because we are going to increase the number that are known from several thousand to over 100,000. And we're going to do this by detecting planets in regions of the galaxy that we've been blind to, around stars that we've been blind to, and in distances from the host star that we've previously been blind to. And this is going to completely revolutionize our understanding of planets around other stars. So this is a little bit of a more technical slide, but I really want to emphasize this because it's easy to say, oh, Roman is Hubble with a large field of view, and it really doesn't do us justice because we're not 100 times better than Hubble. We're more than 1,000 times better than Hubble in the speed with which we can map the sky. But we're also spectacular with the control of the observatory itself. The precision with which our point spread function, which is what something looks like in the detector, is outstanding. And our ability to precisely measure the brightness of things is also outstanding. And the combination of these is what will give us an extraordinary broad science menu. So I've talked a little bit about the cosmology that we'll do. I've talked a little bit about the exoplanet science that we could do. I could give you an entire talk on what we can do with the populations of stars that we're going to precisely measure positions in our own galaxy. How we're going to track populations of stars to understand the distribution of dark matter in our own galaxy. I could talk about how Roman is going to be a very important partner to the upcoming gravitational wave and neutrino observatories in connecting the new multi-messenger astrophysics, observing the sky and neutrinos and gravitational waves, to the universe that we've been observing since the time of the Babylonians. But there's more. Because I haven't mentioned that we have two instruments. Everything I've discussed so far is science that we will do with the main science instrument, the wide field instrument. The second instrument is the coronagraph. And I'm not really going to describe this in any detail, partially because I'm not really qualified to it. But if you imagine you want at some point in the future to be able to directly image an Earth-like planet around a Sun-like star. So let's think about what that means. If you wanted to start and not be quite so ambitious, let's imagine we want to measure a Jupiter-like planet, something bigger, something brighter. That is the equivalent of being able to image a firefly around a lighthouse where the lighthouse is in Los Angeles and we're in DC. And now let's move to imagining what it means if you want to observe an Earth-like planet around a sun-like star. Now you are asking us to figure out how to image one bioluminescent algae around a lighthouse that's in Los Angeles and we're in DC. So this is a really technical challenge. So one way that you can address this is, I think of it as kind of like being magic with physics. So the idea is, a coronagraph is that you find a way to block out the light from the central star. And you do this by putting the light through some sort of a mask that uses the wave properties of light to create destructive interference at the position of the star. And you use the rest of the interference pattern to measure and monitor the wavefront errors. So the system itself consists of a sequence of masks, but also a set of deformable mirrors that automatically change their shape to accommodate changes in wavefront error so that you can keep the whole system stable. You need to have very low noise photon counting CCDs. So the Roman coronagraph is going to premiere all of these techniques. By itself, it will not have the sensitivity to image an Earth-like planet around a sun-like star. But it is going to lay the trail for the technologies that will do that. It's going to demonstrate that it's possible. And if it exceeds requirements, which it's on a path to, it will be able to image the equivalent of a Jupiter-like planet around the star. And we'll be able to study debris lists. But the primary contribution from the Roman coronagraph is to be able to show that we can build and operate deformable mirrors in space. That we can build and operate the incredibly sensitive CCDs and low-noise CCDs that are necessary for this.
Can I ask quickly?
Yes?
Is this something you have or something you're going to have?
It is something that we have. So, obviously it's not launched yet, but it's all the flight components are in place. The optical bench is fully populated. They're in integration, going into integration and test. So it's real, even though it sounds like magic. So I have more that I could say, but I'm at the 30-minute mark, and this is a logical stopping point. So we can stop here and take questions. Okay, let's see.
I was wondering if you could educate us a little bit about the wavelength sensitivity. So, I remember that with James Webb, we were going to be able to measure redshifts and go all the way back to something like 13.5 billion years, within 300 million years of the so-called origin. And with the Nancy Roman, it must have a significant overlap in the wavelength region, but you didn't say anything about where the
I did. So the red edge of our wavelength coverage extends to 2.4 microns. So it's not nearly as red as the James Webb Space Telescope. So we operate in the near infrared. So we're not as focused on getting to the very earliest times. Being in the near infrared, though, it does give us the advantage of avoiding the attenuation looking towards the center of our galaxy. It is appropriate for the wavelength range where the dark energy measurements are most interesting, which is a little bit later. So there's overlap, but we don't go nearly as red.
Thank you.
The point at which the universe transition from decelerating to accelerating. The way you describe dark matter and dark energy, were they somehow closer to 50-50 at that point, or do we not know?
Yes. So dark energy, dark energy has a much greater impact on the universe now than it did far in the past. And you could think of it of it being like a constant property of space. So as the universe has expanded, there's more of it to push. And I've about reached the end of what I know about dark energy, but I don't feel so bad about it because I don't think anybody else does either.
So because the volume got bigger, there's more of it.
That's one hypothesis, but realistically, we actually don't. I mean, dark matter is relatively well understood. Dark energy is
Where do you park it?
right. It's really a mystery. The fundamental nature of what it actually is.
That transition point from, again, is it just a coincidence that that's about the same time that our sun and Earth were formed? Is that just...
It's probably, yes. So the balance between dark energy and dark matter wouldn't have a local implication.
I'll let you speculate again. But when you're going to do the experiment where you have a wide angle and you expect to see some lensing, but is that assuming that there are going to be pockets of dark matter in the galaxy, or that, could it also be that the galaxies get uniform, we won't see this? Do they, how far advanced have you heard that?
we have a precise knowledge of how much dark matter there is in the universe. And that's because the presence of dark matter puts an imprint in the cosmic microwave background. And it's, in the early universe, the presence of dark matter being there, interacting the way it does or doesn't, had an impact in how the early structure was happening very early in the universe. So from the CMB measurements, we know how much dark matter in the universe there is, and we know that it doesn't interact like ordinary matter. So that 27% is solid. So the question that we're addressing with Roman is what is the spatial distribution of that dark matter as a function of time? And measuring that will tell us something about dark matter itself. So if the dark matter, for example, is a heavy kind of particle, then it's going to clump earlier, and you will see structure forming earlier in the universe than if the dark matter is a very light particle that is moving close to the speed of light. So the measurements that we, do I think we're going to see the weak lensing? I'm sure of it, because we have seen we're not going to be the first people to have done weak lensing measurements to measure the structure of dark matter as a function of time. What we're going to be is measuring it to a much greater degree of precision.
But the dark matter, the lensing we're seeing now is due to neutron stars or black holes.
No. So the lensing that we're seeing now that we see now in weak lensing experiments is lensing of background galaxies from matter in clusters of galaxies between us and them. It's not small things. It's big things.
What's your science data rate to your onboard storage, and what's the science data rate to the ground?
I know that, it's just gone flying in. So I'm not going to be able to give you an actual answer because I've forgotten what the number is, although Kevin can probably tell you. But you can get an estimate of what it must be. Because if we're surveying the sky 1,000 times faster than Hubble with the same angular resolution. We have something like 1,000 times the Hubble data rate. So we're much larger than Hubble, we're much larger than Webb. Which means that we're changing the paradigm for how we expect scientists to interface with data. So our model is not that somebody is going to go to our archive, download all the data to their laptop and do the analysis, because it would take them a long time to download the data, and they probably wouldn't have the CPU power on their laptop to do anything meaningful. So instead, we're putting in a science platform where the user comes to us and they run their analysis code in our environment with the data in place. So we download the data, it will go into the cloud, and then it will stay there. And so we do have to move some, obviously the cloud doesn't exist in L2, so yes, we have to bring the data back. But once it gets here, we try and minimize how much it moves around from that point forward. And I'm sorry that I don't have a precise
I think it's
answer.
over 11 gigabytes per day.
Something like that.
Are there enough astrophysics physicists available to analyze the data, or are you going to depend on AI?
So yes, that's the other thing. So relative to Hubble, the amount of high-level processing that we do is much, much greater. That our assumption is that, of course, if we're seeing a billion galaxies, there aren't a billion astronomers. I mean, there's barely a billion people who can look at those one at a time. So we will have a variety of high-level pipelines that are designed to produce data at the catalog level that will be suitable for most of the science that people want to do. There is a lot of development in the area of machine learning and AI to exploit to lay in place methods to exploit the data in a variety of different ways. And they range from things to identify different kinds of planets. The Galaxy Zoo, which is kind of a combination of human power and AI. Sorry, let me explain what Galaxy Zoo is. Galaxy Zoo is a crowdsourcing project where they use people looking at galaxies, characterizing them, to take advantage of the fact that our eyes have very good pattern recognition. So the idea is that you give a galaxy to 10 different volunteers. They have guidelines on how to categorize them. You kind of go with what the majority opinion, and it's turned out to be a very effective way of classifying large numbers of objects. Obviously, with Roman, the number of objects will be far too high. So what the team is planning to do is to use AI to identify all of the normal galaxies and ignore those, and present to the humans the subset of galaxies that are interesting or unusual or harder to do something with via AI, and use crowdsourcing for that fraction. So that's an example of kind of using the sort of volunteer community and AI in a combined way. Yep.
Any other questions?
Can you touch on the subject of the fate of the universe? And say a little bit about that? How this ties into it,
So, yes. So the idea is, let me go back, is I convey the impression that we have no idea what dark energy is, but that doesn't mean that we don't have underlying theories and things that we're trying to constrain. So, if what you're looking at here, Kevin's already alluded to this. This is time along the x-axis and the scale of the universe on the y-axis. So, if this is a straight line, the universe is expanding at uniform velocity. So, what you see is a acceleration during the beginning of the universe, a period where we're kind of expanding the way that we had originally assumed the universe behaved. And then we've got the surprise happening close to the current time, which was an acceleration. So the question is, can we combine the information that we get from understanding the evolution of structure, which is telling us about how things come, which is the pulling in force, to precise measurements of how dark energy, the things pushing things out, has changed as a function of time, to get information on whether we think the acceleration is going to continue to happen, in which case, the universe is going to spread apart, or continue constantly as a function of time, or maybe collapsing later.
Let's thank our speaker again.